Right. The first part of this question asks us to estimate some statistics, and the first one is the mean of the dependent variable. So we have to establish what the dependent variable is. Looking back here at the graph, the dependent variable is generally shown on the vertical axis and denoted as y. What is the mean of y? Well, again, looking back at the graph, we can see that the y values range from a high of about 26 to a low of about 4. If we project all of these y values back, there's no obvious skew in the distribution. Seems fairly symmetrical, so estimating the mean to be roughly halfway between the maximum and minimum seems reasonable. So that would be a high of 26 plus a low of 4 divided by 2 to halve them, and we'll get an answer of approximately 15. The second statistic is the standard deviation, also of the dependent variable y. So our rule of thumb for the standard deviation has been that we will take the range, which is the maximum, minus the minimum, and divide it by 6. And this is somewhat crude, but we are assuming in doing this that roughly 99% of the values are falling within 3 standard deviations either side of the mean. So this 6 is 3 either side, 2, 2. And we're also assuming that we're roughly seeing the maximum and minimum values in the sample that we have. If we use these values, we'll get 26 minus 4 is 22 divided by 6. It's a little bit less than 4, but I'll say approximately 4. And whenever I ask a question like this, particularly of the standard deviation, it's difficult to estimate just by looking at the data, but it is useful to have some feel for how some numbers that you can look at might translate into a standard deviation. So we will apply the Fisher-Black rule of efficiency. Fisher-Black was a financial economist who is most famous for his option pricing model that he devised with Myron Scholes. You probably will have heard of that option pricing model. And anyway, Fisher-Black in another paper said that he thought that an efficient market was one such that prices are correct to within a factor of 2. That means that so long as the market was within in the range of half of the true value to double the true value, he thought that the market was actually doing a good job, and perhaps that was as good a job as it could do, given the uncertainty in the financial markets. Anyway, so long as your answer is within that range, between half of the true standard deviation and double the true standard deviation, then I'll be happy. In this case, I think the true standard deviation, if you knew what all these y values were, works out to be around 6. So we're in the right ballpark, the right magnitude. The correlation coefficient between x and y is next. Now, this is a measure of the linear association between x and y, roughly how close to a straight line the scatter plot looks. You know that if it's a perfect straight line, then we will have a correlation coefficient of positive 1 or negative 1. If it's upward sloping like this, it'll be positive 1. If it was downward sloping like this, an inverse relationship, we would have a correlation coefficient of negative 1. This one is upward sloping, so it's definitely positive, and it's not too far off a straight line. So an answer of, say, 0.7, moderately strong, but definitely positive, would be a reasonable approximation here. It turns out that if you knew the exact values, it's actually a bit closer to 0.8. But again, if your answer is, in this case, if you said anything from 0.5 up to about 0.9, I think I'd be reasonably happy. The second part, part B, says estimate the equation of the population regression line that's shown and show your workings. So up here we have a line drawn, and in order to define a line, one way of doing this is to work out its slope and then its y-intercept. Well, we can already see what the y-intercept is down here, bearing in mind that this is the x equals 0 here. So when x is equal to 0, y looks to be equal to about negative 2. So I'm going to write my answer here, negative 2. The equation of the line, sorry, is going to be y is equal to ax plus b, or in this course we'll see it more often as b1x plus b2. And I've actually worked out the b2 here, the intercept. And to work out the slope, it's the rise over run, and to get the best estimate you would take the extreme most values that you can see. So this value here is x equals 0, y equals, we're saying, negative 2. This one up here is x equals 20, down here, y equals approximately 30. And rise is the change in the y values, so that will be I'm going to do slope. The rise is 30, take away negative 2, and the run is 20. These points, the x and the y, have to correspond, so they're both coming from there. Take away 0 is equal to 32 divided by 20. That is going to be 1.6. And so our answer would be approximately y is equal to 1.6x. That's the b1, the slope, minus 2. Right. Part C then. Says estimate the disturbance term for the 30th element of the population. Back to our graph. Here is the 30th element, down here, so it's x is about 15 and y looks to be about 17. And to find the disturbance term, that's the difference between the expected value of y given x, so that is up here, and that is going to be, I will say, roughly 23. So the difference between these two things here is actually the disturbance term. So it's the difference between the expected value of y given x and the actual y value. And, well, I'll just write it here. It's, in fact, the order is the actual y value, so 17, this is u, is equal to 17 minus the expected value of y given x, which is 23. So it is negative 6, approximately. And note, it's got to be negative. It's negative because the actual value is less than the estimated value. And over to part D, it says use Excel's rand between function to randomly select 4 elements from the population other than the 30th element. So in Excel you would type equals rand between. Then you want to pick numbers based on the index. That was one thing that you had to work out. So index numbers between 1, that's the low value, and 29, so we don't include 30. And this function will just randomly pick a number, an integer, between 1 and 29 inclusive. And copy that formula so you get 4 numbers produced. I actually came up with the values of 16 to 23, 17. The next question says to circle these elements on the graph. So here is 16. And it says include 30 as well. 2 down here. 23 here. And 17 here. And then it said draw a line of best fit through those. So something that is following the general path of these points. Now by my eye, the general path is probably something like this. There's not a great deal of precision in what I'm doing right now, but we're trying to draw by hand a line which we think follows the pattern of these 5 sample points. The key thing is that your sample, if you draw a line that fits that the best, it won't necessarily be the same as the population regression line. And the last bit says F, using what you've just done, show the residual for the 30th element of the population. So the residual is going to be the estimated value of y, which is this one here, plotted across here, compared to this actual value of y, which we saw earlier was 17. So it's going to be this distance here. And the calculation is the actual value of y, which is 17 as before, minus the estimated value of y based on the sample regression function, and by my calculations that looks like it's about 21. So again, we're going to get a negative value, but smaller magnitude this time, negative 4. So it is the same sign as the disturbance term in this case. It doesn't necessarily have to be, though the residual is an estimate of the corresponding disturbance term, so you would usually expect them to take that same sign. It is possible, and maybe you had a unique sample in the one that you chose, that we could perhaps get a regression line that looks possibly like this. Just imagine that the 5 points we chose were this one, this one, this one, this one, and maybe this one. So in that case, our sample regression line might have looked really nothing like the population regression line, but now our estimated y value would actually have been less than the true value, and we could have come up with a positive residual, notwithstanding that the actual disturbance term was negative. Okay, so the key thing at the end there is just to say that a residual is an estimate of the true disturbance term that we generally won't know, but because it's an estimate of that value, we would normally expect it to have a similar magnitude and the same sign.